Hello, it's Scott Manley here, back at NASA Ames, taking a look at the Advanced Supercomputing Facility. Given that Ames is in Silicon Valley, this makes total sense. Using NASA's most powerful supercomputers, the team at Ames specialise in things like computational fluid dynamics, which are essential to developing future aircraft and rockets. And when you can combine these high-fidelity computer simulations along with Ames' world-class wind tunnel facilities, you can see why this facility is pretty much at the forefront of a lot of NASA research and development, enabling a lot of testing and simulation to be performed and problems identified before you commit to building a full-size version where changes become a lot more expensive. So I got invited to a tour of this facility along with a bunch of other creators who are all at OpenSauce. NASA put together a day-long tour for us, and have you already seen a couple of videos from that?
I'm not going to spend a ton of time here, but it's a good place to kind of
whole lot of Cray history here.
A lot of
You're like a good customer for Cray.
and Silicon Graphics.
Yeah, SGI. Yep.
Right. Well, the first significant kind of major supercomputer that moved into that from the old vector machine into this massively parallel paradigm. But the early supercomputers, back when I started, now they're the power of your phone has more.
Yeah, I think my phone has teraflops of power now, which is like 2000. It's ridiculous.
Yeah, I started back there. So it's, yeah.
NASA Ames' history with supercomputers starts in the 1970s with a computer called ILLIAC-4. This was the Illinois Automatic Computer, and it was originally developed in collaboration with the Department of Defense and the Advanced Research Project Agency to be installed at the University of Illinois. But then concerns were raised by students saying that it would be used to develop nuclear weapons. There was a whole lot of anti-war sentiment, and ultimately what happened was the computer ended up getting moved to NASA Ames instead. It ended up being very late, way over budget, and they only built 1/4 of it. But even then, when it was used to solve the right kind of massively parallel problems, it was clocking more than 50 megaflops. It would also be the first supercomputer connected to the ARPANET, which would of course eventually evolve into the internet. Cray supercomputers would arrive in the early 80s and they'd go through a few iterations of these. The Cray 2 would have performance of about 2 gigaflops. They had a couple of thinking machines hardware, CM2 and a CM5 that had something like 16 gigaflops of performance in the mid-90s. And by the year 2000 they had many silicon graphics systems, the fastest one clocking in at 400 gigaflops. Almost all the systems they installed after this were racks of silicon graphics equipment. By 2002, they had a teraflop capable machine. And now the fastest machine they have is the Pleiades. It began life in 2008 with 400 teraflops. Now it's something like 7.5 petaflops. That's almost 1 billion times faster than the ILLIAC-4.
We run the agency's primary supercomputers that serve all of NASA's mission. And I like to say, if you've seen it on TV, in the news, on the web, if you've done stories on it before, some part of it probably might be our compute floor. And so we're going to give you a little walk of our compute floor. We're going to show you some amazing science instruments and talk a little bit about what we do with our supercomputers. We'll start down here. This is kind of a traditional data center on one hand, so what you might see in industry with our supercomputers upstairs using the technology where we have cold water and we bring in power, we do cooling in a traditional way. And if I could point you it's a different tour, but the poster there, what we've started to do is move to a modular supercomputing infrastructure. And we're taking things that look like shipping containers and we're putting computers in there. And in this climate in the Bay Area here, the thing that's great about it is we don't have to do chilled water. We don't have to basically use air conditioning for our computers. We can use passive heat transfer, take advantage of the climate, and we put water directly on the chip for cooling, and then we can move all of the heat off of the compute IT and just get rid of that into the atmosphere without boiling or evaporating water. So we save about 25% of our total costs by moving out there, our electrical costs, right? How much extra electricity do you put in the system based on what goes into the IT to solve problems? This data center here, we're at about 1.25. So for every kilowatt of IT compute for science, we pay about 25% extra. Out on the pad, it's about 5%, so 1.05. So we pull a lot of kilowatts through here, a lot of megawatts. We run 24/7, 365 with a wink and a nod. We do annual downtime for maintenance once a year, but otherwise we're running all day, every day. And so that extra 20% is huge for us as far as operating and then being able to take advantage of our area and do more science and engineering.
What's the power load of this building then?
The power here is about 4 megawatts. So our facility is about 6 or 7. We are deploying a new system now that I don't know if you drove by the pad on the way out. Our first prototype module is right across the street here. If we go out the side of the building, you'll see it. It's got screens on the top that are heat exchangers. They look like the coffee filter. If you drive down the road, we have a 1-acre concrete pad. There's 2 of these large shipping containers. They're actually compute modules. Bolted together. We're deploying a brand new system that came in last week. It'll be NASA's fastest supercomputer. We call it Athena, and the vendor is just delivering it, and we're in the process of hooking up the cooling, plugging it in, so that the delivery team can bring it up and turn it over us to make secure and make ready for science. Yeah, and so the new system is maybe 1.5 megawatts. Right now, the facility can take up to 3.
Do you have a 4 megawatt UPS?
So, yes.
For how long?
So, on the back side of this building, we have three RUPS, so they're rotational UPS. And so we pull power from the grid and we put it into a flywheel, which does have parasitic draw, so we lose a little bit for that. And if utility goes down, then the momentum, the energy in the flywheel gets us through until the generators kick on. So we can run indefinitely as long as we have diesel. A lot of diesel. 4 megawatts is a lot of diesel. Yeah. Generally speaking, our outages don't last that long. We just need it to ride us through power sags. Yeah, and in that case, it works. When it's working, it works quite well. But it's closed system. Okay, yeah, and on the modules. And if it gets hotter than we can cool, we can drip tap water over the heat exchangers. Yeah. But then instead of 10,000 gallons, right, got a lot better. So it is going to be quite loud. I'll do my best. We'll take some time to do questions after if you want. But we'll just come right in the corner and then we can talk about what's in these racks. Sound good?
Sounds good. So yeah, you get the idea. It's very hard to hear anything this guy says in the middle of a server room surrounded by all these computers. How many computers? Well, this is the Pleiades supercomputer. As of 2016, it is something like 250,000 CPU cores across 161 racks, 4 different generations of Intel Xeon processors, 900 terabytes of memory. There's also an offloaded tape storage facility, which handles hundreds of petabytes of data. And yes, the guy running the facility confirmed that it will in fact run Doom. But of course it's primarily used for scientific computation. If Mars is involved, you can bet that it's something to do with re-entry rather than demons invading from another dimension. But to really appreciate the kind of data that this produces, you need an amazing display system, and that's where they took us next. Yay!
We call this physical zoom in and physical pan in. So welcome to the NASA Hyperwall. This is one of our primary instruments for exploring and interrogating massive multidimensional data sets. At its core, the Hyperwall is a supercomputer. 128 powerful compute nodes sitting up on the machinery floor, which you might have seen when you were up there. Those nodes are interconnected and interwoven into the broader NAS framework, so we connect to every machine at the NAS. And then on each one of those nodes, we strap on a 27-inch 4K monitor, which together make up our 16 by 8 billion pixel display system. So the back end, the compute, allows us to do all kinds of real and near real-time data streaming, processing, analysis, rendering, you name it. And then the front end, and this room actually, has proven to be this very powerful tool for collaborative exploratory analysis of massive data sets. So we have our science collaborators come out for days, they camp out, they lose track of time, they don't see the light of day. And it's our role within the visualization team to help develop these environments that allow them to explore their data in new ways. To give you an example of the kinds of data sets that we're working with, this is the ECHO model, estimating circulation and climate of the ocean. It is our highest resolution, best estimate of what our oceans are actually doing. And ocean scientists all over use this model as kind of a data observatory to study all the different data dynamics, all the different ocean dynamics from kind of the major current systems like the equatorial current and the boundary currents, the Kuroshio Gulf Stream region, to kind of these eddies, ocean eddies at all different scales from 100 kilometers down to sub-kilometer scale, or the spreading rings, kind of these internal tides that propagate up from the bottom of the ocean floor. You can imagine all the different dynamics. I learn about a new one every day that I work with these data. And so it's these ocean scientists that really work with these data, and we help them. Just to give a couple more points of context, you're looking at sea surface speed, so brighter is faster, and we're showing 1 ocean second per day. So this strobing that you see along the borders, those are semi-diurnal tides. So we're seeing 2 tides per day. So this is kind of the brief introduction to our Hyperwall system. And from here, I'll actually turn it over to Dr. Lara Rash, who will discuss a recent Hyperwall.
Yeah, that was a great initial reaction as we continue to pull up some images. So my name is Lara Rash. I'm an aerospace engineer here at NASA Ames. I am tied to the unitary plane wind tunnel. And more specifically, I am working on developing the systems necessary for unsteady pressure-sensitive paint.
So interestingly, the first presentation made on the video wall wasn't actually a computer simulation, but it definitely involved computers. This was the unsteady pressure-sensitive paint system. Essentially a special type of paint on wind tunnel models which changes colour depending upon the air pressure it's feeling. Traditional wind tunnel models will have tiny holes in them which lead to a pressure sensor, and you'll read out a few points in the model, but using this you can read out pressure changes across the entire surface of a model. And while this is actually based on an experimental model, actually processing the data from the high-speed cameras takes a lot of processing power, and so it is still very much dependent on NASA's supercomputer capabilities. So for this visit, they very specifically talked about a problem with the SLS, which they were trying to address using this technology.
What are we looking for here?
So you can click different frequencies. You can rotate the model around as well. So
okay. So, and we can zoom in because this is the streak that we're discussing. These streaks here, right?
And you can imagine this is a very thin piece of metal too, so it's impossible to actually fit some instrumentation inside.
Yeah.
But if you zoom in, and because of PSP and it's an optical diagnostic, I can get you what that pressure data is on that surface of the streak itself.
And this is with the pressure-sensitive paint that you're right.
Yes.
So I'm just curious. Do you have any? Can you explain how that works for?
Yes, absolutely.
Because you're the expert.
Pressure-sensitive paint is an optical diagnostic, meaning we use high-speed cameras in order to acquire the data. So you'll notice as you were rotating around where I have these dark areas, that's because I cannot get the camera to see underneath the booster itself. So there's no data present there. But the paint itself consists of a rough base coat that's solid white. And the roughness is important because it increases the surface area. It's one of the ways that the unsteady formula gets you a faster time resolve, because the pink part that you see on the outside of the model is called a luminophore. And this gets excited at a particular wavelength of light. So I have 40 lamps that I install in our 11 by 11 foot transonic test section. And so at 400 nanometers, these lights excite the luminophore. So the photon is shaking around, it's all excited. And then depending on what the partial pressure of oxygen is. So it doesn't really matter what kind of air combination that you have, it's really reacting to that partial pressure of oxygen specifically. So if there's more oxygen, then this photon is going to get oxygen quenched back down to the ground state. But if there's less oxygen, which means less pressure, then that photon is going to be able to emit. And then that emission is what my camera is being able to see. And again, that's why we have the raw data for you. So you can actually see those high and low pressures. So it's an inverse relationship relative to brightness. So I want to emphasize it is not changing color. It is just changing intensity of brightness. And we do some in situ calibration. So we can change what the static temperature is in the wind tunnel when there's no air blowing. And I take some camera images. So now I know, okay, at this uniform pressure, because I apply the paint myself, it is a toxic paint, so please don't do this at home. But I'm respirator certified, so I don the respirator, the full bunny suit, and I spray the paint directly on the model once it's fully installed inside of the test section. So that's one of the joys of having an 11-foot by 11-foot test section. I can do that. We do turn out all of the lights, yes, and we do isolate any ambient light source. So even though the paint itself gets excited at that 400 nanometers I mentioned, just the ambient light will degrade it over time. So it's called photo degradation. So the longer that it gets degraded, eventually you run out of those photons that can actually emit. So you do have to do a reapplication of the paint. In a production setting like this, I'd say I can get about 8 to 10 continuous hours before I'd need to shut things down and reapply. So Unitary operates in a 2-shift system. So we work on grave shift and day shift. So usually, because of the limited resources, this is restricted to a single shift. So, but I just apply the paint once, that's good enough for the entire shift. And then I'll come in the next day and apply more paint for the next day of testing.
Hi guys, I'm one of the greedy CFD people that always likes more. So I'm pretty excited actually on all the things that Larry has shown from experiments, because that gives us more insight on our simulations and data that we generate. I also have a big benefit in comparison to her. I don't need safety measures, no gas mask, nothing like that. All I need is a stress ball, because you guys probably know writing code gets frustrating. My workstation is expensive. I don't want to throw it out my window sometimes. So that's very important for us. But otherwise, yeah, this is a simulation that has been done using computational fluid dynamics with our in-house NASA developed lava solver, which stands for Launch, Ascent, and Vehicle Aerodynamics. And this is a CFD simulation. So just imagine you have a CAD, and then you wrap in the computer a computational mesh around this. And at each of those nodes of the mesh, you solve the Navier-Stokes equations. In this case, we have 4.5 billion nodes. So that is a massive simulation that we run off the solver. Just as a reference, if I would take an instantaneous snapshot of one of these visualization simulations and write out a volume data, that is around 60 gigabytes or 20,000 pictures on your iPhone, roughly. And you can imagine how many pictures we need of this to make a video like this. So it's really very important that you use state-of-the-art computer science, use the systems, and you guys saw the systems upstairs to make them really efficient. And the way this was actually motivated to run this specific simulation is we learned about the cool experimental new things and things that were done. And then my division chief came to me, he said, hey, there's this really cool new project going on the Hyperwall. Can we do a CFD simulation side by side? And I asked him, yeah, sure, when do you need it? Well, tomorrow. And you can imagine with these kind of simulations, just even today, most commercial codes and other codes, they would take for big simulations like this months to run on a supercomputer. We were able actually with our lava solver in-house to crank them out on the fly, write data. Our visualization team pulled the data while we were writing it and made the video. So we were able not just to make one of these videos and simulations overnight, we tried quite a few things here. And what you see specifically here is actually in grayscale, that's a density gradient magnitude on a centerline slice. And then you see the skin friction on the surface of the vehicle. And here is just a comparison on the bottom. That's from a Schlieren image from experiments, which is somewhat similar to this density gradient magnitude. I'm going to show you guys a couple of other visualizations next. You were asking questions about the strakes.
And so at this point, we all got a bit of a revelation. Something that had been a bit of a mystery for SLS watchers had been the addition of 4 strakes near the forward attach points for the boosters. So these strakes were like 6 foot long. They looked like aerodynamic devices. They had been added after booster stacking. And the official explanations were all pretty vague. It was something about, suppressing vibrations, which could be a problem for the booster. And of course, inquisitive people like myself wondered how these small things could have a big enough effect on the rocket that they would add these long after the booster had left the factory and while it was in the vehicle assembly building.
So you see here now a slice that's going right through the centerline plane between the booster and the main stage. On top is a simulation without the strakes. On the bottom you see strakes, and you see density gradient magnitude. And I think everyone can easily see the difference between them. I would not want to sit in that launch vehicle while it's flying without the strakes. That is going to be very rocky. So just by adding these strakes, you can see how nicely aligned those structures become. You don't have these huge vortices shedding off. And the biggest problem is the resonating frequency of these vortex shedding is unfortunately aligned with some of the structural components which caused some issues. So that is a huge difference. And the benefit is now, with our simulations, we can literally look everywhere we want, everywhere in the volume field, and look at details, not just single microphones in some locations. We can really look at it in very detail and then compare it with experiments. And this really, not just for nice visualizations, this really gives us a chance to learn new things, improve designs. And the fact that we can crank these simulations out overnight now is really a big, big game changer, which has been enabled through GPU development. So all the solver is completely on GPU, which really made a huge difference. Just going to show you guys some more videos on this side. Yeah. If you actually now see here, this is the same run, but a different way of visualizing it. So what we show here is, again, the skin friction on the surface, but here we inserted some ISO contours around this region specifically. And you see here is where the strake is. So now the strake and the flow coming in creates this vortex that goes underneath it, and you can really observe lots of these flow features, and then eventually look also at a side-by-side comparison between experiments of some of the surface pressures. Any question to that?
Is this about Mach 1.2 or something?
I think this case was the 1.2 case.
Okay.
Yes, that's
judging
correct.
by the angle.
Yeah, you see all the shocks here too, right? There's so many different shocks, and then the interaction of that vortex coming into the shock, and then you see things that are happening all over the place.
As I'm understanding it, you've got these strakes that are angled, and so what you're getting is like a vortex shedding happening off the tips here, and then that's constraining this oscillation because you've got these these energized vortexes. Yeah. And again, you got to understand there's a booster that's sitting between us.
It's right here.
And so this is sort of getting constrained into almost like a two-dimensional layer. So this is a great representation.
Yeah, so that's the benefit of those simulations, because a camera is going to have a hard time doing here.
Yeah, you could build a transparent booster for your model, right?
I've been trying to convince some people to do that for a long time, because I'm greedy, I'm a CFD person, I want more. I haven't gotten it yet.
Put cameras inside the model so it can see these gaps.
I would love that.
Ideas.
You can really do cool things. You can also do a mode decomposition on that plane now, and then focus in on specific frequencies, and then frequency band filter this, and just look at the structures at one specific frequency, and get back in the time domain. And now I can figure out, okay, what is actually happening here? Where are they interacting? What can I do with this?
So I now want to explain this again, now that I've had the sort of benefit of hindsight. This is showing the forward attach point of the solid rocket boosters, and you can see that it generates this wavy motion downstream of it. This is a well-known phenomena in fluid dynamics known as the von Karman vortex street. What you're getting is when the flow speed is just right for the obstacle, then you get a vortex that sort of gets shed off one side, and then that vortex changes the flow on the other side and causes a vortex to get shed off the other side. So you get these vortices going in opposite directions flowing downstream, and we see this around mountains, buildings, all sorts of obstacles. And on the SLS booster, we were seeing it at exactly the right frequency to excite structural problems. So on the SLS solution, they added these little vortex generators, the strakes, and what happens is on one side, high pressure air spills over the top, and that generates a swirling pattern, a vortex, which in this case, the axis of rotation is aligned with a booster. So this creates basically a long whirlwind which is going downstream. And that sort of is higher energy, so as these vortices try to shed, it sounds like they bump into this and it stops them oscillating. And the reason I recognize this is because I did a video a couple of years ago about using these kind of vortex generators on wings to reduce span-wise flow so that the stall characteristics of wings are different. Yeah, I'll link that video. Anyway, this was a really cool presentation because it showed how they used the physical experiments with the pressure-sensitive paint and the computational capabilities to solve a problem, and they actually produced a solution. So we were left with this big video wall. What else did we get to do with it? Well, we got to take a look at Vera Rubin images pretty much at native resolution. This is what happens when you have a billion pixel display at your disposal. Since there's actually computers attached to all these screens, technically this is a supercomputer in and of itself because it can do a bunch of native processing. It was an extraordinarily cool experience to go and look at this thing and be able to like pick out the redshifted distant galaxies without having to manually scroll the whole thing around in a smaller window. So once again, thanks to NASA for putting this together for me and all the other creators. This actually, the specific one, was a great way of showing the integration between their experimental capabilities in the wind tunnels and their computational capabilities. I actually have a lot more video from this. I will share it on my Patreon if you're interested in getting the raw feed. Also, there's one other part of this tour, the machine shop, where I realized that there were other creators there who definitely knew more than myself about that. And I'm not sure I'm going to make a video about that, simply because I think that any one of them could do a better job than me. But then again, that's why I like going to places, to meet people that can do things better than me. I'm Scott Manley. Fly safe.